Okay, this is the second part of the fundamental theorem of calculus. Basically, what we want to try to prove here is that if f is differentiable on the closed interval a to b, and f and the derivative of s is integrable on the closed interval a and b, then the integral of the derivative of x is no more than the difference of the evaluation of f and b and f and e. Okay, if we use the definition of the Riemann integral, we can define p as the partitions, right? The partition is the finite numbers that we can divide the function. So we have the interval from a to b, we have the function here f, we have the derivative of the function, right? And we have the finite xi, which are the partition. Okay, if we apply the mean value theorem to each of these partitions, we can guarantee that there exists a point ti inside of the open interval of the partition such that the difference between these two is the multiplication of the wherever we have from the i's, right? The stream of the partitions multiplied by the evaluation of this t, right? So basically, if we see the example here, these two, this is, let's take this partition from i-1 to xi, right? This is basically the same thing here. We have a t somewhere where this point is exactly the same as the line between the 2 points, right? So there is a point f of ti, right, of the derivative of t that is pointed to this ti. Okay, so if I can substitute these two by ti, okay, then now that we have this, we can include this for all the partition that we have, right? And we will have a summatory, but this summatory, where is coming from this summatory? Basically, we have this f of b minus f of I, right? Which is exactly the last term, the last number of the partition and the beginning of the partition. But we can include some zeros, right? This zero could be the previous number to the xn, which will be xn minus 1, and so on, right? Minus 2, and all the way until we get to x0, right? So then, if we have all this sum, we will have basically this difference, the xi minus the xi minus 1, right? The evaluation of the function on this term of the partition. But we say it here that this difference is wherever point we have, which is the derivative of f on ti, which is the point where the derivative have the same slope, multiplied by the distance of the partition, right? So we substituted this part here. It's exactly the same, but with different terms. Then what? We see that the lower sum, I mean, this is not the lower, this is the infimum point of the derivative of s is less than or equal than the point on t, which is less than or equal than the supreme number of the evaluation of the derivative of f for all the i's, right? That is coming from the definition also of the Riemann integrals. We have it here, right? In this case, my infimum is the lower point that f has an evaluation. The maximum one, in this case, is this one. Is this one that is here? Let me point it here. It's not exactly the same point in the string, but we have the infimum and supreme numbers, and we can have basically exactly these same summatories, but using the infimum and the supremum, right? And this is what we have it here. We have it in the middle, the summatory that we obtained it before, but we say it that we can substitute this part by the infimum and by the supreme, and that is actually the definition of the lower Riemann sum that we have it here, right? So, but if we have this lower sum but any arbitrary partition P, we can say that this is the lower sum as it is, and this is the upper sum, right? The lower integral and the upper integral, sorry. And then, by the assumption the derivative of f is integrable, it means that this value is exactly the same as this value. If they are the same, then this difference is equal to the integral of f of the derivative of f. Therefore, they are equal to the difference of what?